University Video Communications, with the sponsorship of Silicon Graphics Incorporated, welcomes you to this edition of the Distinguished Lecture Series, Leaders in Computer Science and Electrical Engineering. Forest Baskett is Vice President of Research and Development at Silicon Graphics Incorporated. While at SGI, he helped design the multiprocessor structure at the heart of the Iris Power Series workstations. He received his BA in Math from Rice University and his PhD in Computer Science from the University of Texas, Austin. In this lecture, Dr. Baskett presents a position for cache-coherent multiprocessors by discussing the shared memory model, effective private caches, efficient data sharing, efficient synchronization, automatic parallelization, comparison with vector architectures, performance results, advances in compiler technology for cache locality and parallelization, technology trends, and future evolution. Forest Baskett.
Today, we'd like to discuss shared memory multiprocessors with cache-coherent caches. The notion that we would like to present is that structures such as this type of multiprocessor are in fact an excellent solution to the general purpose computing problem, particularly for science and engineering computing problems. Before we go into this, it's worthwhile to look at what is still somewhat widespread conventional wisdom that such multiprocessors are not in fact good general purpose computers. So what are some of the things that people typically think about the liabilities of multiprocessors? First, we can look at RISC processors and we can see over the last several years a speed up in individual processors of about 80% per year. And so that, together with the design time for a multiprocessor, makes people believe that by the time you design a multiprocessor with today's RISC processor, tomorrow's RISC processor will have arrived and will outperform your multiprocessor on non-parallel tasks. In addition, people believe that many applications are difficult to parallelize, and that, together with the additional overhead that a multiprocessor structure does undeniably add to a uniprocessor application, we get the notion that, in fact, multiprocessors are special purpose machines, not general purpose machines. That's the conventional wisdom. The new wisdom, the wisdom that we'd like to persuade you of, is that, in fact, for a new processor, the multiprocessor product development time is on the order of 6 months longer than the development of a system around a new uniprocessor. And in addition, being able to upgrade to a faster version of an existing processor is just as easy for a multiprocessor as it is for a uniprocessor. So the argument that faster uniprocessors will supersede multiprocessors is a difficult argument to sustain. In addition, the applications can, in fact, often be parallelized with new compiler technology, particularly vectorizing compiler technology. Vectorizing compiler technology has been developed over the past 12 years to the point where many applications can, in fact, be vectorized, and the technology for that vectorization, in fact, will enable us to parallelize applications. Then, if we look at the cost of a processing system, the processor and its cache represent 25% or less of the total system cost, and that means that multiprocessors are extremely cost-effective structures. If we then look at what we get from building a multiprocessor, we get two fundamental benefits. The first, easy, obvious one is that we get a machine in which we can get increased throughput. We can run multiple applications on multiple processors in an independent fashion and take advantage simply of the cost savings of the total system structure. But on the other hand, we can take applications, we can often parallelize them, we can run a single application on multiple processors and get substantial speed up as well as an economical structure. So these are the two advantages of multiprocessors that we can get with this kind of relatively simple structure. Now, in order to investigate the notion that parallelization for individual problems is in fact possible with vector technology, let's look for a moment at some results that we can achieve with the 24 Livermore kernels. This is a collection of a variety of scientific problems that were put together at the Lawrence Livermore laboratories, and I'm going to go through the names of these kernels so that you can see the span of scientific problems that these kernels cover. Now we take these kernels and apply a conventional vectorizing compiler with a conventional vector machine. And what we find is for the 24 kernels, the convex compiler of a few years back on a C120 is able to vectorize quite effectively about 15 of the 24 kernels. For some, very little change from scalar to vector, but for others, almost an order of magnitude improvement in the performance of the kernel. If we take similar compiler technology on our multiprocessors, do the same kind of experiment with 1 processor, 2 processors, and 4 processors, we see that most of the same kernels that vectorized will in fact parallelize, and we see about 13 of the 24 kernels with substantial performance gains from the multiprocessing structure with automatic parallelization. Now, given that we can in fact parallelize applications, why do we want the processors to be put together in a cache-coherent fashion? Well, certainly the first benefit is with cache coherence among private caches of different processors, the programming model is the very simple shared memory model. The programmer believes he understands what's happening. There's a single memory. The fact that there are private caches doesn't influence the programming structure at all. But at the same time, private caches are part of the structure behind the scenes, and they provide the additional instruction bandwidth and the additional data bandwidth that are absolutely required in order to make the processors really useful. In addition, the private caches are a lot cheaper than a large honking main memory system that has to deliver the bandwidth to a variety of processors or to a vector processor. And private caches are technologically inevitable. As we go to more and more integration, we'll find on-chip caches. The on-chip caches are associated with individual processors, and so private caches are something that we need to be able to take advantage of in a graceful fashion. Now, fortunately, properly designed coherence protocols are relatively simple and can have low overhead. Here's a simple model to illustrate the gains that we get with private caches in terms of processor bandwidth for data as a function of the number of processors. We add processors, we also add private caches, and the total bandwidth goes up as the number of processors goes up. So this is the fundamental notion that we're trying to take advantage of. I'll use the Silicon Graphics Power Series as a design example. It's been a successful machine design and can illustrate and justify some of the principles that we've gone over. There are other systems that have also been successful and that could be used in a similar fashion, such as the ones made by Sequent and Encore. Here the plan is to look at the logical characteristics of our systems to illustrate the feasibility of the principles, but also to look at the physical characteristics to help us understand the engineering design constraints and the technology available at the time of the initial design. This design started in October of 1986. The use of the physical systems has also led to some new and somewhat unexpected design principles that we'll certainly cover at the end. So our engineering design goal is to build a multiprocessor out of commercial RISC microprocessors that would be competitive with some more specialized small vector processor machines that were being developed by some startup companies at the time of this initial design. And the startup companies were Ardent and Stellar. The engineering design constraints were that the system had to fit in an office. And what this fundamentally means is that we have to come up with a system that consumes less than 1,000 watts. because that's all the power that you can get out of the wall in your typical office. The other fundamental design constraint imposed was that we needed usable configurations of less than $100,000. Now, these are somewhat arbitrary constraints, constraints that were dictated by the structure of the company and the structure of the product family and the structure of the sales force. And at the same time, these are somewhat arbitrary constraints that provide a framework in which you can come up with an engineering design and answer a lot of questions in a fairly quick fashion. Now, if we're trying to compete with some small vector machines, let's look for a moment at how well vector machines do on scientific problems. Here I've listed a number of different vector machines and have given the cycle times of the machines, the megaflops of those machines on the popular Linpack 100 by 100 benchmark, the year of introduction, and also a measure called cycles per flop. Now, the measure cycles per flop is an attempt to get at the efficiency of these machines at delivering floating point computations that's somewhat independent of the technology. It's a measure that's comparable to the cycles per instruction measure that's often used when evaluating RISC machines for scalar computation rates. So cycles per flop gives us a measure of floating point computation that can span a wide range of technologies. It's sort of the architectural efficiency of a particular machine. Now, the interesting thing about this collection of vector machines is that the cycles per flop number hovers around 3. Most of these machines have a cycles per flop rating of about 3. On the other hand, if we look at scalar machines going back in time, a fairly successful machine in the science and engineering domain was the original VAX 11780, which had a cycles per flop measure of about 30, nowhere near 3. The VAX improved over time, getting down below 20. And then when the modern RISC machines came on the scene, we started seeing some substantial progress in cycles per flop as the architectural efficiency of these machines for floating point computations really became apparent. And we're getting down today where we have scalar machines that can deliver cycles per flop measures on the order of 2.5. If we graph out this trend, we get a graphical picture that looks something like this. It says that vector machines have been pretty steady at 3 cycles per flop. Scalar machines have been rapidly approaching that number, and today we'd say that we're there, and that we have a match of a modern scalar machine versus the vector machines in terms of the architectural efficiency for this particular benchmark. Now, this is not the whole story. The Linpack 100 by 100 benchmark is in fact a fairly small benchmark. A larger one is the Linpack 1000 by 1000 benchmark. And if we look at the difference in the performance of vector machines on the small benchmark versus the large benchmark, typically we'll find that there's another factor of 3 to be gained by going to the larger problem. That is, the vector machines don't reach full efficiency on the small benchmark. When they get up to the large benchmark, they're getting on the order of 3 times more performance. What that means is that for large problems, the cycles per flop number for vector machines is on the order of 1 cycle per flop, and the scalar machines still have a way to go to catch up with them. The technology trends are that the scalar machines are in fact headed in that direction, that the graph that we looked at showing the scalar machines catching up with the vector machines is in fact an accurate representation even for large problems. Now, going back to our goal of using RISC processors to build a multiprocessor that could compete, given that we believe that the technology is there, let's look at the design constraints, particularly the power budget. Going through the RISC processor that Silicon Graphics was using at the time, the MIPS architecture, R2000 processors, with that particular processor, It was possible to build two processors in a single cabinet and still satisfy our power budget. The R3000 was close to coming on the scene at the time of the design. Silicon Graphics managed to persuade MIPS to make a few small changes to the R3000 that in fact made it much easier to build multiprocessors with. And with the same power budget, we could build a 4-processor version of the MIPS R3000. So, looked like we could meet our power budget. Looked like the floating point technology was there. What were the details with respect to the architecture? The MIPS R2000 and 3000 are microprocessors that require write-through caches. That is, when the processor writes into the first-level data cache, that write needs to be reflected on back out the back end of the first-level data cache. And over the years, we've clearly learned that write-through caches generate so much write traffic to main memory that using a write-through cache in a multiprocessor structure is really not a feasible or desirable way to go. So that led to a second-level data cache, actually for two reasons. But the first reason was to be able to soak up the write-throughs from the first-level data cache, and then have the second-level data cache function as a write-back data cache to reduce the main memory traffic. At the same time, the second-level data cache gave us an additional duplicate tag store. And that tag store could be used to perform bus washing operations on the main memory bus for a Snoopy cache protocol. This was an important additional feature since the first-level data caches are primarily used up in servicing the processor. The tags are busy all the time doing matches for loads and stores from the processor itself. So that second-level tag store is a critical part of the overall structure. So in order to have a Snoopy cache protocol, we've got two basic types to look at. The first type is the write broadcast type. In a write broadcast Snoopy cache protocol, changes to a shared cache line are broadcast over the bus to all the other caches. So if we've got a shared line, we broadcast changes to the data, all the caches update their contents, and we have a cache consistency, coherent memory structure across all the private caches. The other primary type of Snoopy cache protocol is the write and validate type, in which changes to a shared cache line cause a special bus operation, address invalidate transaction, to be performed on the bus before the write completes in an individual processor. Thus, a shared line becomes a private line when it becomes dirty. Now, with these Snoopy cache protocols, the write broadcast protocol we know is useful for synchronization operations. Because change data gets broadcast immediately, if we're doing a synchronization operation, we have an operation that minimizes waiting. The latency is the lowest possible, and if we're trying to get processors to cooperate rapidly, fast synchronization is really a desirable attribute. On the other hand, a write and validate structure is useful for data sharing operations. We're trying to minimize the data sloshing on the bus, unnecessarily moving data back and forth from one private cache to another. So given that one of these types is good for synchronization and the other type is good for data sharing, what do? Well, we need fast synchronization and we need efficient data sharing, so we just do both. Now, this is a block diagram of our processor structure. On the left, we have the CPU and floating point unit pair connected to their individual private instruction cache and data cache. Those caches are connected to some buffers, and then those buffers go through a second-level data cache and then on out to the main memory bus, what's here called the MP link bus. On the very left, we also have something called the sync bus. Now, how do we implement a Snoopy cache protocol that enables us to do it, to have both protocols? There are a lot of ways in order to achieve this goal, and the way that we achieved it was to have, first of all, a special kind of memory, part of the physical address space, 64,000 words, designated as test and set variables. When a particular processor would perform a read or a write operation to one of these physical addresses, those read or write operations would become test or set operations on that special memory. The test and set memory itself was physically replicated on every processor. Now, it turns out that this is a fairly inexpensive process with today's memory technology. It required one memory chip per processor. But in addition, the set operations arbitrate for the special bus, the sync bus that was on the left, and new values are broadcast into all copies on this bus. So the memory is physically replicated, and changes are broadcast and copied into all copies of the location. And of course, one critical element to make all this work is that this memory has to be marked as non-cacheable. So the structure of the system was that processes can request of the operating system pages of this special test and set memory. Those pages can be mapped into the virtual address space of a process. And at that point, processes that are sharing those pages can then synchronize with each other without further operating system attention. That means that synchronization operations can be performed without system calls at memory read and write speeds. On the other hand, on the main memory bus, we want to use a write and validate protocol. We solve the synchronization problem by using a special memory with a write broadcast protocol on a special bus. Go back to our main memory bus where we want to share data. We'll use a write and validate protocol, and with that, a very simple form in which a cache line can have one of four states: invalid, clean private, clean shared, or dirty private. So when we have a write into a clean shared line, we're going to initiate an address and validate operation on the bus. All of the other copies of that cache line will move from clean shared to invalid, and the processor doing the write will have its cache line move from clean shared to dirty private. So the second level tag store is now in operation to watch all the bus operations and then to keep its cache lines in the appropriate state. The basic multiprocessing principle that we're trying to address with the write and validate bus protocol is the notion that each processor is responsible for a different part of the result set for a parallel application. And the structure that we achieve is one in which the shared input is replicated in the private caches, but the output, which is segregated, is in fact private. And with that, we minimize the bus traffic necessary to support the parallel application, and we minimize the need for bus bandwidth and memory bandwidth. These last two minimizations are extremely important if we're to meet our budget constraint. One note about these protocols is that they work well and their implementations are quite simple, provided we have physically addressed caches. If we're looking at a system that has virtually addressed caches, the problems are much more difficult. And dealing with the MIPS architecture and the implementations which use physically addressed caches, fortunately, we didn't have to deal with the much more complex issues of virtually addressed caches. There are some compromises in between physical and virtual addressed caches, but the simplest case is with physically addressed caches. Now, bus bandwidth. This is one of the primary consumers of the power budget, and it's one of the primary consumers of the dollar budget. Faster buses are better if you can afford them. but they're not cheap. Now, at this point, at the time of beginning this design, the question was how much bus bandwidth did we need? Well, the conventional wisdom at the time, some conventional wisdom that had been developed over the years, particularly at the national laboratories working with vector machines on a wide variety of applications, was that we needed approximately 8 megabytes per second of bus bandwidth for each sustainable megaflop for each processor that we could deliver. So if we were looking, as we were, at a 4-processor system with each processor able to do about 2 megaflops sustained, and we needed 8 megabytes per second for each of those megaflops, that meant we needed a bus with a bandwidth of about 64 megabytes per second. Well, 64 megabytes per second was apparently what we needed, and doing the engineering, it looked like we could afford it, but just barely. So we set out to build a system with a 64 megabyte per second sustainable bus bandwidth. The only problem here was that we were then building a system with no headroom. We knew faster processors were coming, and if this conventional wisdom held true, we knew we were going to have a problem when we got to those faster processors. But we had to move forward, so we did. An important note about the engineering here: the interface between the first level caches and the second level cache and the second level cache and the main memory bus is an asynchronous interface. Now, lots of hardware engineers don't like asynchronous interfaces, particularly when they're between synchronous subsystems. They introduce overhead. But with that asynchronous interface, the processor and the first level caches were running on an individual processor clock, and the second level caches, the memory and the I/O subsystem, were running on the memory bus clock. So we had a clear division of clocking disciplines, and we had a structure in which the processor modules could be field upgradable as the faster processors that were coming became available. This is, in fact, an extremely valuable feature for a commercially viable computer system, and has proved to be extremely useful to us. Now, let's see how well all this has worked. Here's a well-known application, Abacus, a finite element analysis program, and some performance data on a particular benchmark for this application. The bar on the left is the performance of one of the processors of our first 2-processor system on a large data set, completing in 27.5 hours. Going to a parallel version of this benchmark, running on 2 of those processors, we get that down to 16.5 hours. And then as we move forward to a 4-processor, 25 megahertz R3000 system, able to reduce this benchmark down to 3.4 hours. And finally, moving to 7 processors at 25 megahertz, we get this down to 2.7 hours. So this is a case in which we've taken a particular benchmark, gotten an improvement in the runtime of a factor of 10 over a time span of about a year, and simply by going to more processors and faster processors in basically the same multiprocessing structure. A few more examples to show what this multiprocessing structure is capable of. Gromos is a molecular dynamics application. DNA5 is a particular data set for that application. And as we look at the performance of this application on that data set for 1 to 8 processors and look at the speed up as we go to more processors, we see that we get close to a speed up of 5 as we get out to 8 processors. Here's the same application with a larger data set. And notice that with the larger data set, we get a better speed up. This is an example of a phenomenon that arises in multiprocessing where the size of the problem is important if the problem gets to be small, because the overhead associated with each of the pieces can in fact become an important part of the total computation time, and the speed up that you achieve with multiprocessors may in fact not be what you desire. So bigger problems are better. Progressive radiosity, another application that we get substantial speed ups on. And here's the large LINPACK benchmark, 1,000 by 1,000, very well behaved benchmark where we're getting close to a speed up of 6 on an 8 processor system. This is a ray tracing application from the Ballistics Research Laboratory. Here the speed up is getting, for an 8 processor system, is getting well above 6. This is a 2D complex fast Fourier transform. And here there's again there's a range of performances depending on the problem size. The lowest green line is in fact a 256 by 256 problem size. The red line is a 512 by 512 problem size, and then the blue line is a 1,000 by 1,000. And it's clear that the 256 by 256 is really too small a problem for 7 or 8 processors, but the 512 by 512 and larger are quite substantial and achieve pretty respectable speedups. Vortex is a computational fluid dynamics application where we're looking at particle flowing through a fluid field. It's a very parallel application. The particles are distributed among the processors, and then very little interaction occurs. And in fact, because of that nearly perfect parallel structure, we get nearly perfect speed up as we go to more and more processors. So if we put all those things together, we get what we might think of as a performance envelope or a range of expectations for parallel applications. We find a lot of applications of different types that can in fact benefit from this kind of parallel processing. The amount of benefit varies, but for the most part it's respectable, and it can go from your 8th processor being worth about half a processor on up to 8th processor being worth a full processor. Now, at the time of this writing, the systems that we're looking at have 8 processors at 5 megaflops each. But we're still running these systems in the same system configuration with a 64 megabyte per second bus. And remember, our rule of thumb when we started was that a system like that would need on the order of 320 megabytes per second. So what's happened? What's happened is we've discovered how to use private caches more effectively as we've developed these systems and developed these applications. The private caches are relatively large and fast. In this particular structure, the second level cache is 256 kilobytes for data. But more importantly than the size has been the locality of these algorithms. We have improved the locality of algorithms as we have gained experience with cache-based processors. And in fact, cache-based processors are slowly changing the conventional wisdom of the necessary memory bandwidth. The primary reason is the development of what are called block method algorithms, or in some cases tiling algorithms, basically the same thing, for a large variety of important scientific and engineering problems. Now let's look for a moment at block method algorithms. Here we're looking at the standard sort of naive matrix multiply algorithm, 3 nested loops for one processor in single and double precision, the lower 2 lines, and 8 processors in single and double precision. For one processor, we're getting on the order of 2 to 4 megaflops for single and double precision. But with 8 processors, we're only moving up to about 7 megaflops for double precision and about 12 megaflops for single precision. Not very respectable. And in fact, if we look at the speed up curve, as a function of the matrix size, we see that we're getting speedups on the order of 2 to 3, or 2.5 to 3. Not an effective use of 8 processors. Now, if we switch to a blocked method in which we take the matrices and we look at small subblocks, multiply the subblocks together, and then combine the results, we find that we can improve the cache locality substantially, and as a consequence, the single processor results are quite a bit higher for the block method than the single processor results for the standard method. But even more exciting, the parallelism available in the block methods goes up very substantially, and we find that we're getting performance for double precision in the range of 30 megaflops for this configuration and single precision in the range of 40 megaflops. The speed-up curves really highlight this for this particular blocked matrix multiply algorithm, speed up in the range of 7 for an 8-processor system. So we're really getting a payoff from this kind of algorithm. Doing a comparison, here's the 8-processor results for the standard algorithm on the bottom, the 8-processor results for the block method on the top, and then the comparison of the speed-up curves. So the exciting thing about block method algorithms is that at the moment, this is a technology that is developing among the algorithms community, but it's a technology that is receiving substantial attention from the compiler development community. We're at the stage where compilers are going to be able to automatically develop block method algorithms from the more naive, straightforward algorithms that we would prefer to deal with. What this means is that we're getting to the point where compiler technology is going to move past vectorization into a realm where cache locality is improved and multiprocessor parallelism is improved, often to the extent that individual algorithm writers will not be able to keep up. That will have compiler technology that can do fabulous jobs taking advantage of this particular kind of computer structure. So we think we've got a computer structure that not only is exciting for the problems that we've got today, but a computer structure that's in tune with where hardware technology is going and is in tune with where compiler technology is going. Thank you.